Question number one, we know that the two triangles are congruent to each other. So basically, do the CPCTC, all of the corresponding sides and angles are going to be congruent. So if we're looking for which statement is not always true, we're looking for what parts do not correspond. So in number one, AC is the first and third letters. It's right over here. BD, also first and third letters. They do match up. Moving along, CE, second and third letters, so it corresponds to the second and third letters, which is DE. And if you take a look here, if you imagine reflecting this one over, this will land on this. That is true. They do correspond. EAC, congruent to EBD. EAC, second, first, third. Second, first, third is EBD, so that's all good. And if you imagine taking this one and flipping it over, this angle will land on this angle. And finally, ACE, first, third, second. First, third, second should correspond to BDE, not DBE. And if we take a look over here, ACE, DBE, those don't correspond. If you flip this one over, this will land on this. This will not land on this. And always use the letters of the triangles to figure out what corresponds, because sometimes it can be tricky to see visually. This was straight, number two, straight from one of the cooldowns we had in class. Which method could be used to prove the triangle's congruent? A lot of people got this wrong because they did not mark the diagram. They tell us angle B is congruent to angle D. And they also tell us AC bisects angle ABD. So angle BAD. So angle BAD is what's getting bisected. So BAD, that's this whole angle here. And if it's getting bisected, it means it's being split into two equal halves. So I'm going to mark those two equal halves, those two equal parts. We have this half and we have this half. And notice how the two triangles are connected, they're touching. They both share side AC. AC is part of this triangle. AC is part of this triangle. It's congruent to itself by the reflexive property. So we have angle, angle, side. And answer choice 2 is totally wrong. AAA does not prove triangles congruent. And if you ever forget that, just think about equilateral triangles, right? Equilateral triangles have 3 equal sides, so they have 3 equal angles. And since all angles of a triangle make 180, 60, 60, 60 make 180. So here as well, 60, 60, 60. So both of these triangles are equilateral. They both have the same angle measurements, but the side lengths are clearly different. So equilateral triangles show how two triangles could have congruent angles, all the angles congruent to each other, but they still don't have to necessarily be congruent. So AAA does not ever work to prove congruence. Cross that one off immediately if we're talking about triangle congruence. In the diagram below, 4 pairs of triangles are shown. The corresponding parts are labeled. Congruent corresponding parts are labeled. Which pair of triangles cannot be proven congruent? ASS, or in the reverse, SSA. However you looked at it, it's the same thing. It does not work. We don't want to be writing bad words on our geometry test. So A is our correct answer. We can go through the rest of them and see why the other ones are right. Angle, angle, side, that does work. ASA, that does work. Right triangles, congruent hypotenuse, a congruent pair of legs. HL, it is. Moving on to the next one, we have triangle FGH. And it tells us angle F is congruent to angle H. GF is x plus 40. HF is 3x minus 20. And GH is 2x plus 20. Since I have two equal angles, due to the converse of the base angle theorem or the converse of the isosceles triangle theorem, if the angles are equal, the sides opposite, so the side and this side, are also congruent. Once again, that's not the isosceles triangle theorem, that's the converse. The isosceles triangle theorem or the base angle theorem says if you have two equal sides, then you know the angles opposite are congruent. Here we started with the angles and we drew the conclusion about the sides. So it's the converse because it's the reverse. So since I know that these two sides are equal, I can set them equal to each other. Subtract x, subtract 20. And now it's asking for the length of GH. The x value is there, that's the trick. 2 times 20 plus 20 is 60 when we plug in. Let's take a look over here. We're going from dm to dl, and we're going from el to em. So clearly I see we're going smaller. We're going from a longer segment to smaller segments. So it's going to be subtraction. So goodbye 1, goodbye 3. Let's think about what we're going to be subtracting. So let's start with dm. dm is turning into dl. Let's think about how we can get dl. If we take dm, let's think about what we need to subtract away to get just dl. Well, we need to subtract ml. Okay. On the other side, we're starting with el. And let's see what we're subtracting. We're just going to use a different color. So here's el. And let's see what we're subtracting to get em. From L to M, LM. I don't want to use yellow to write LM. So I'm going to move this over slightly. I'm going to write a bit smaller so it doesn't come off the screen. So notice here, when we're subtracting, oh, and EL minus LM is going to give us EM. That's by substitution. This minus this is that. This minus this is that. So we're starting with two congruent segments. DM and EL are congruent. That was provided to us right here. And we do need to know, in order for our subtraction to work, that what we're subtracting is also congruent. So we need to know that ML is congruent to LM. ML and LM are the same segment using the same two letters. Here's LM, here's ML, they're the same thing. So that is reflexive property. If we were writing a proof, before we could do subtraction, we would need to say that ML is congruent to ML or ML is congruent to LM by reflexive property. So we have answer choice number 2. So people lost points because it wasn't clear where your angle, where your number was, that it wasn't in the angle. Like if you're placing angle 1 in ROA, it can't be here, right? I don't know what that is. Angle ROA is right here. It's this angle. Angle DTO, if you put the 2 over here, like, no, that's not right. Angle DTO is here. Angle ABD is here. AO congruent to DT. Here's AO. Here's DT. OR congruent to DB. Here's OR. Here's DB. Angle TOA. TOA congruent to angle TDA. OT parallel to DA. And AR perpendicular to OR. That means they form right angles where they intersect. Or right angle where they intersect. That's right angle. Sorry, my box is a little messed up over here. Okay. Use the properties of rigid motions to explain why the triangles are congruent. You can't just say reflections happened. You need to use properties of rigid motions. So you might have realized that two reflections could have been used here to map the triangles onto each other. If you're going from this triangle to this triangle, one possibility is a reflection of the x-axis followed by a reflection of the y-axis. If you're going from this triangle to this triangle, one possibility is a reflection of the x-axis followed by a reflection of the y-axis. So I'm going to use that in my answer, but I do also have to mention what I know about rigid motions or rigid transformations in order to answer the question. So I'm going to write here, since reflections can be used to map triangle ABC onto triangle XYZ, the triangles, oops, I can't type today. The triangles are congruent because rigid motions or rigid transformations preserve side lengths. They keep side lengths the same. Before and after reflection, side lengths are the same. And angle measures before and after a reflection. Angle measurements are going to be the same. Corresponding angle measurements are going to be the same. Creating congruent figures. So I just put mine all in one sentence. That's like a really long run-on sentence, but whatever, it accomplishes the job here. Oh, for this one, I forgot the vertical angles. I didn't see that on my screen because I can't view it all at once. So let me do that now. Here's a pair of vertical angles. So for the vertical angles, you could say angle OAR is congruent to angle DAB because that's a pair of vertical angles here. You could have also said angle DAO and angle BAR. That also would have worked in this situation. Those are two congruent vertical angles. Vertical angles are always congruent to each other. Okay, we need to explain why the lines are parallel. So something very, very, very important here. So let me just fill in the givens. Make sure you always fill in the givens. Some people were saying this is 50, so this is 50 because they're corresponding angles. Or people were saying that something else has to be something else because they're alternate interior angles. You cannot say that because you do not know the lines are parallel. If you knew the lines were parallel, A, B, and C, D, then you can use all of that. You can say this and this are this measure because of corresponding angles. This and this are this measure because of alternate interior angles. But since you do not know the lines are parallel, you cannot use that because it is not true unless the lines are parallel. What we need to do, what our goal is we need to find one of those relationships. If we can find congruent alternate interior angles, or congruent corresponding angles, or congruent alternate exterior angles, if we can find one of those relationships, then we could know for certain that the lines are in fact parallel to each other. So that's what we're trying to get at here. So I'm going to use things I know for absolute certain, and that is that vertical angles are congruent. They're always congruent to each other no matter what. And also, that's a linear pair. These two angles form a linear pair, they're supplementary. So that means I know that this one has to be 65 because 180 minus 115 is 65 degrees. Things I know for sure. That's what I'm doing here. Things I know for absolute certain. Okay, I missed a given. All givens are there for a reason. I needed this 50 because that's vertical to it. They gave me this 115 because I can find the angle that's supplementary with it. They gave us this given for a reason too. It wasn't there just by accident. It's not there just for practice marking the diagram, but even though you should mark it in the diagram, it's there because that given tells us that this triangle over here is an isosceles triangle. And when a triangle has two equal sides, we know, due to the isosceles triangle theorem or the base angle theorem, whatever you want to call it, the angles opposite those sides are congruent. So be careful here because this triangle is oriented weirdly. This triangle is oriented sideways. So it's like this. So be careful. The angles across from the congruent sides are the ones that are congruent. So matching that up to what we have here, these are the congruent angles, opposite from the congruent side. So this one's 65, we know it already. So this one's also 65. And since all three angles of any triangle sum to 180 degrees, 65 plus 65 is 130. So this angle has no choice but to be 50 degrees to make the 180 degrees of the triangle. And now look. We have found congruent alternate interior angles, which proves the lines parallel. And yes, since this is an explanation question, anything that you write in the diagram does not count towards your score. You can have all this nice stuff, you don't get credit. The Regents exam doesn't give you credit. You need to explain where all of those measurements came from in your explanation. So let's do that. Since angle EGB and angle AGC are vertical angles, they are congruent. So measure of angle AGC is 50 degrees. Since angle DIG and angle GIH are supplementary, the measure of angle GIH is 65, since 180 minus 115 is 65 degrees. Since GH is congruent to IH, angle HGI is congruent to angle GIH, since if a triangle has two congruent sides, the opposite angles are congruent. And I'm going to put in parentheses, that is the base angle theorem, also known as the isosceles triangle theorem. So angle GIH is also 65 degrees, because before I mentioned angle, I mentioned angle GIH. GIH, that's this one, so I need this one, HGI. Hard to keep track of all these angle names. HGI. There we go. Okay. Since all angles of a triangle sum to 180 degrees, the measure of angle GHI is equal to 50 degrees, since 180 minus 130 is equal to 50 degrees. Since the measure of angle AGH is equal to the measure of angle GHI, and they're both equal to 50, AB is parallel to CD, since alternate interior angles are congruent. If alternate interior angles are congruent, lines are parallel. We need to prove the two triangles congruent. That's what the proof statement says. I got to figure out how to do that. Number one is always given. That's always what you start your proof with. Some people did not write their full givens. You do not get credit for that on the Regents exam. On the Regents exam, they actually do not give you any points for writing the givens, but you will lose points if you don't have them, because the givens are your starting point for all your conclusions. Without the givens, you don't have anything, right? Then you're just literally making stuff up. So the givens are necessary because they're everything that you have to work with. They're the basis for everything that you're saying. That's a lot of givens, but a lot of it's really helpful. Number two is talking about right angles. There was nothing in our proof before this except for the given. So obviously that has to come from the givens, but I don't know which given. But then I see the perpendicular symbol, and I know that perpendicular lines form right angles, right? That's how I know right angles are formed. I see the perpendicular symbol, and I know that perpendicular lines form right angles. That's angle ABC, because AB and BC were perpendicular, so they form a right angle where they intersect. And that's also angle DEF right over here, because DE and EF are perpendicular, so they form a right angle where they intersect. Now we're saying those right angles are congruent. Take a minute and ask yourself, why are right angles congruent to each other? Well, because they have the same measure, right? Because all right angles are congruent. They're the same. And now it's telling me EB is congruent to EB. Going to also mark it in my diagram. And that's the reflexive property. And I don't really understand why we need that right now. But when we get to the addition postulate that's being used in the next reason, I think it'll be a little bit more clear. In step number 6, I'm jumping because I don't know what I'm adding. But I'm jumping to 6 because this is the result of my addition. Because after addition, we usually have substitution, which tells us what the result of our addition is. This plus this is this. This plus this is this. So this is telling us what we're getting. So we're getting from our addition, we're getting AB congruent to DE. So let's see what we got to add together. I'm starting with, back to my givens, because I used, and I can check off the givens as I go. We already used the perpendicular givens, right? Because we got the right angles. Now we got to use this next one. We're starting with AE being congruent to DB. Now I marked it, now I check it, now I used it. So I have AE. And when I think about what I need to add on to AE to get AB, that's EB. AE, stick on EB, we get the full segment AB. And on the other side, we have DB. And we're trying to make DE. So to DB, if we stick on BE, then we make DE. So notice, in order for addition to be valid, we have to start with congruent, and we do know that AE and DB are congruent. That was given to us. That's how we marked it. That's why that was necessary. You can't just randomly add things. Addition works if you start with congruent and add congruent. So you can't just be doing craziness. The only way your sums are going to be congruent is if the things you're starting with and the things that you're adding are congruent to each other. And that will make congruent. You start with congruent and you add congruent, it makes congruent. So here we're starting with congruent. We need to be adding congruent. So we do need to state in our proof that EB is congruent to BE, or you can say EB is congruent to EB because it's the same thing, they're the same two letters, and that's why the reflexive is needed before this addition. I'm going to write the addition that we just did on the side. I like to do it on the side. For me, writing it bigger on the side helps me a little bit. This plus this is that. This plus this is that. We're replacing the addition with what it actually gives us, which is substitution. I was seeing craziness here. I was seeing subtraction. Addition and subtraction are not going to be in the same thing that you're doing, right? It's one or the other. You're either making things smaller or you're making things bigger. Okay. Now I see that they're talking about two angles. So we're off of the addition. We're talking about two angles. And let's talk about, first of all, the result of the addition. From the addition, we ended up with AB, which is a full side of this triangle, and DE, which is a full side of this triangle. So in the two triangles so far, we have this side on each of them, and we have the right angles on each of them as well. For the angles next, I'm going to mark them in the diagram, CAB and EDF. And I'm having a hard time seeing the relationship between the two, but then I remember I have another given that I didn't mark. AC parallel to FD. And that given's there for a reason as well. If I highlight my parallel lines and my transversal, notice the letter Z. And these angles are in the corner of the Z. So they are alternate interior angles. So here we can put down alternate interior angles are congruent when parallel lines are cut by a transversal. I abbreviated because I'm trying to move fast through this video. You can write out the full words. Alternate interior. And now let's see why the triangles are congruent. Whenever you're showing triangles are congruent, it's going to be one of our 5 reasons. It's going to be SSS or SAS or AAS or ASA or HL, right? It's not some random reason, and it's definitely not CPCTC. CPCTC comes after you prove triangles congruent to say that corresponding sides or corresponding angles are also congruent. So after you prove these triangles congruent, if you then want to say, okay, since the triangles are congruent, I want to show that AC is congruent to FD. Well, that would be CPCTC. Or after you prove the triangle's congruent, if you want to say, I want to prove angle C is congruent to angle F, that would be CPCTC. But to prove triangles congruent, you can't prove them congruent with CPCTC. You prove them congruent with one of these 5 methods, and the one that applies here is angle, side, angle. Next, this one we had to write from the beginning, but as I always say in class, please do not jump into writing your proof. Please mark your diagram and figure out what's important. So first, my goal. My goal is to prove PT congruent to RU. I know that PT is a side of this triangle, and RU is a side of this triangle. I'm always looking for triangles. If I can prove these triangles congruent, then I can prove this. How? Using CPCTC. Once again, if I can prove these two triangles congruent, well, then I can prove the corresponding sides PT and RU congruent using CPCTC. So let's see now what information we can get inside these two triangles. Once I know that I'm focusing on these two triangles, it becomes easy because I know that we have parallelogram PQRS. And now I know in that parallelogram, I want these opposite sides to be congruent because that's going to help me. These opposite sides, RQ and SP, are not going to help me. They're not part of those triangles. This will help me. I know in a parallelogram, opposite angles are congruent. That's going to help me. And how could I forget about the last two givens? QT is perpendicular to PS. They form a right angle where they intersect. There's also one here. I don't need that one because I'm interested in these triangles. SU is perpendicular to QR. There's a right angle here. Once again, there's also one here, but I don't need that one because I want the one in the triangles. Now I have everything I need for AAS, and I can follow that with CPCTC to prove that PT is congruent to RU. Let's write this up. I'm just going to write all my givens in the first step. You don't have to. You could break them up. I just don't want to forget them. I'll start with the right angles. I'm going to start with angle RUS. That's this angle over here in blue. And angle QTP are right angles. And that's due from the perpendicular lines in the given. Perpendicular lines form right angles. And since I'm using them for AAS, I need two congruent angle pairs. So I do need to say that these right angles are in fact congruent to each other, because all right angles are congruent. Now I'll put RS congruent to QP. And also, that was one of our angles. These congruent right angles in blue were one of our angles for AAS. So RS is congruent to QP. We know that because opposite sides of a parallelogram are congruent. That's how we knew that. And that's our side that we're using for AAS. And then we have angle R congruent to angle P. And we know that because opposite angles of a parallelogram are congruent. And that gives us our last A for AAS. I know here in the proof, we put it in an angle side and an angle. It doesn't matter the order that you put it in the proof. What matters is the order it's actually in the triangles. And that's why you need to mark your diagram, because somebody could very well write ASA, but it's not. In the triangles, it's angle, angle, side. So that would be wrong. So please make sure that you do mark your diagram. So we have triangle RUS congruent to triangle QTP due to angle, angle, side. And then our last step could then be that PT is congruent to RU due to CPCTC. Because once the triangles are congruent, the corresponding sides are also congruent due to CPCTC. For the bonus, and this one is not that bad of a question, so definitely it should be part of the corrections as well. So for the bonus, they tell us that CA is congruent to CB. They tell us that angle PAB is congruent to angle PBA. Oh, wait, that's not the angle. PAB, PBA. And we need to prove triangle EPA congruent to triangle DPB. So these are the triangles that we need to prove congruent to each other. Already in those two triangles, the vertical angles stick right out to me. Vertical angles are always congruent, so that gives me an A to use. If I take a look at the whole triangle for a second, triangles, if a triangle has two equal sides, it also has two equal angles, right, across from those equal sides. So if we translate that to this triangle over here, the big triangle, CAB, has two equal sides, so its base angles are equal. And look, these whole angles are congruent, and these parts are congruent. So if we take the holes and we get rid of these pieces, then we'll be left with the angles that are just inside the triangles that we're interested in. So basically, if we take the whole big angles and we subtract off the parts that we don't want using subtraction, because they are congruent to each other as well, we're starting with congruent and we'd be subtracting congruent, we can end up with the congruent that we need. So that's going to give us, and I'll just use a different color because too many markings here. That's going to give us these angles in blue. So that's going to give us another angle in the two yellow triangles due to subtracting. And then finally, in this inner triangle over here, from our givens, we know it has two equal angles, angle PAB and angle PBA. And just like if a triangle has two equal sides, it has two equal angles. Well, if a triangle has two equal angles, it has two equal sides, the converse of the base angle theorem. And that's these sides. That would give us angle, side, angle. Angle, side, angle. And that's it. Let me write this up. Start with my givens. Okay, I'm gonna do the subtracting first. I'll do the vertical angles last because that's the most straightforward. So angle A, this whole angle was congruent to angle B. And that's because the triangle had two equal sides, so the opposite angles were congruent. If a triangle has two congruent sides, the opposite angles are congruent. And that is the base angle theorem, or the isosceles triangle theorem. Okay. Now we got to do the subtracting. Subtraction. And I'm going to show out my subtraction here. And I know that what I want to end up with is angle EAP, because we put that angle in blue, congruent to angle DBP. And that's going to be by substitution. Substitution always follows addition or subtraction because we're replacing what we're adding or what we're subtracting with what it actually leaves us over with. So we show out our subtraction, and then we say by substitution, this minus this is that, this minus this is that. So we always show that subtraction out. So the large angles that we're starting with are angle A and angle B. And when you subtract, you start with bigger, because otherwise you get negative, and you don't want to get a negative angle. That doesn't even make any sense. And we're subtracting the piece that we don't want, the congruent pieces that we don't want. So PAB and PBA. Angle A, take away angle PAB, leaves us over with angle EAP. Angle B, take away angle PBA, leaves us over with angle DBP. So far, that gives us one of our angles for proving the triangle is congruent. Now we need the side. AP is congruent to BP. And that's because the inner triangle here in red had two equal angles, therefore it has two equal sides. If a triangle has two congruent angles, the sides opposite are congruent. And that is the converse of the base angle theorem. If you just wrote base angle theorem, you'd be marked incorrect. That's why it's better to just write it out in words and just say what you mean. So that gives us the side that we're using for angle, side angle. And then finally, the last thing that we need is to mention the vertical angles, because we need that last angle. So that's going to be angle EPA congruent to angle DPB. And we can write over here, intersecting lines form congruent vertical angles. And then finally, of course, we end our proof with what we're trying to prove now that we have the information in our proof that we need to prove the triangle's congruent. And just like our plan stated, we show that by ASA.